Hello everyone, can you hear me?
Yeah,
I
I can
can
hear
hear
you.
you.
Okay, nice. So today I'll talk about operational amplifiers. So already you should have learned these operational amplifiers in your class, right?
Yes, that's what we just learned.
Okay, so I'll give you just a brief overview here. So um, what is operational amplifier? You already know it's an amplifier. Is basically a combination of electronic circuit elements, and it is used in different cases. For example, in electronic components like radios, or like where you need some amplifiers to apply. Like you have an input signal, you want the output signal to be amplified, or maybe you want to add several signals, and maybe you want to subtract two signals, something like that. And also it is used in case when you need the integration to do. So operational amplifier can operate in linear mode, and it also works in saturation mode. So I'll talk about it, what is linear mode and what is saturation mode. So in saturation mode, the voltage, output voltage will be fixed. It will not be increased after some point, something like that. We'll talk about it. So if we want to know the basic things about the operational amplifier, it's kind of a black box here, right here. So you have an input circuit here, you have input voltage, and this black box is giving some amplified output at the this terminal here. Like that amplified output is actually G times the input signal. So if your input signal is Vs right here, and you using this operational amplifier right here, so your signal is basically amplified G times in the output. But depending on different combination of the input signals, like different point of connection, like you have inverting and non-inverting amplifier points here, so the output voltage will be like reverse, or it will be like as the input signal. I mean, the phase shift will be maybe 0 or maybe 180 degree. So it depends upon the connection right here. So where do you find these operational amplifiers? In radios or guitar amplifiers, even in motion detectors, cell phones, or different kind of sensors. And in stereo systems, you will see this. But what is inside the operational amplifier? Inside, you see, if you think about a simple black box, that black box is basically this entire part here. Actually, this complete part, if you think about a black box right here, and you have a VCC here, maybe it's a plus or minus. So you have two VCCs, and this is ground, and this is output, but you have two inputs here. So this complex circuitry in the middle is giving the functionality of the operational amplifier. So you don't have to worry about this internal circuitry. You just think about it has two input terminals and it has VCC. You know, every electronic circuit or every electronic device, you need to be connected with the power supply, right? So in this case, the VCC is the power supply, and also it has a ground terminal. And why are you using any device in any electronic circuit? Because you want some output, you want some value to see, and that's why this is the output terminal. So this is the symbolic representation of operational amplifier. You see this complex circuitry in between, like it's inside. You don't have to worry about it. Only thing is this is a positive input terminal and this is the negative input terminal, and you have two voltage source here. Actually the two voltage pins, one is we call it VCC positive, and this one is called VCC negative. And this one is basically the output voltage point here. Now, if we make more simplified version of this figure, we will omit these two in every circuit we analyze, because we basically don't need these two. Okay, so to make things simpler, now this is the input terminal that is marked as positive, and this is the input terminal marked as negative. So whenever you see a positive terminal, it is non-inverting. That means whatever signal you put right in this way, a sine wave, say for example sine wave, you will see the same sine wave here, maybe amplified version. If you give here like 1 volts peak to peak, and it has a gain, for example 5, if A is the gain is equal to 5, then you will see like 5 volts peak to peak right here, right? And the non-inverting input terminal, if you connect some signal here, the shape will be similar. Now, if you connect something here in the inverting input, so from the name, you see that it will be inverted. How it will be inverted? So if the input signal is still like this sine wave, it will be in reverse direction. You see, like if we draw it right here, if this becomes your input, and the output, if it is an amplified version, so output will be something like out of phase. So you got the idea, right? So this is the positive direction and this is the negative direction. So this one is your input and this one is your output. So you see a clear 180-degree phase shift for this inverting terminal. Now, as I said, to make things simpler, we remove these voltage sources from our diagram, because in the analysis section, we don't really need this most of the time. So we further simplify the op-amp circuit, the representation, symbolic representation, and finally we come up with this one. And you always draw the symbolic representation in this way. What are the actual pins you have in the operational amplifier? If you buy one operational amplifier from the market, you will see it is something like this. And this one has a name is LM741C, and this is a very common type operational amplifier. And it has 8 pins. What are the 8 pin diagrams basically are shown here? The pin number 8 is not connected to anything else. And as you have already seen, it has 2 power supply points, right? One is right here, which is minus VCC. Another one is right here, which is plus VCC. And this one is the output. And you have 2 input terminals. And that covers your 6 pins out of the 8 pins, right? So you have 1 pin here offset now. Another offset null is here. Why do we need this offset null? We need this offset null. For example, in case of DC amplifier circuit design, in the output you might see some DC offset. What is DC offset? Actually, you will see an added DC in the output section, in the output signal. In that case, you will be needing this offset null to actually nullify the DC offset in the output. Any question? Okay. So this one is basically a very simplest version of this LM741. It can be more complicated, where you may see like 2 of them connected in the same chip, or maybe more than 2. Here you can see like 4 of them connected in the same operational amplifier chip. So sometimes you want to make the use of the space in your circuit board or in your design So, and you need more than one operational amplifier, obviously you will choose this one, right? You don't need to buy LM741, maybe has only one of them and you are using four of them in the breadboard or in the circuit. You just need to use this one, you will get four of them at the same time. So this is the inside the chip. I don't have much to say here. However, in linear mode operation of the operational amplifier, the simplified circuit connection is like this one. So the output voltage, you see plus minus output here. And one important thing is the input is not actually connected to the output right here. So it's kind of virtually connected something. And this input resistance in the input terminal Ri we see here, this is very high for the operational amplifier, and the output resistance, this one is very actually low. It is like in ideal case it is tends to 0. This one is tends to 0, and in ideal case this input impedance is tends to kind of infinity. But typical values are given here, 10 to the power 5 to 10 to the 12 ohm, the input resistance, and the output is 1 ohm to 50 ohm, and the gain is 10 to the 5 to 10 to the 7. Although in ideal case, it is said that this A can be infinite, but actually it's not, right? So even if the input signal here is very low, the output can be very high. And that's why the gain is basically called like kind of infinite. So in the circuit diagram, you have seen two terminals here. One is here in the symbolic representation. So, you know, this one. Now, this connection basically, let me draw the laser pointer here. So this combination, if you put inside the symbol, and you will see this lower figure, where you only see the output here, but this RO is the output resistance, is not seen. I'll show you some circuits here. Here, you see this RF is not actually that R0, so don't mess up with that. This R0 is inside that operational amplifier, that is not connected in the outside. And similar to that, this Ri is the input resistance of the operational amplifier, which is not basically shown in other circuit analysis. Whenever you see the Rs or maybe Rf, they are not Ri or R0, so don't mess up with this. So the simplified version of this circuit is represented here. There is nothing different here. And one important thing to remember that all the voltage we measure here in operational amplifier circuitry are with respect to this common node. I mean this node. Maybe it is VCC plus VCC or maybe minus VCC. So all of them are considered with respect to this common node. Even the voltage sources you are giving here, like VN or VP, they're also with respect to this common node. So don't forget about it. The only thing here, the same voltage source here, the positive terminal is connected to this VCC plus and negative is grounded. Now, if this voltage source is reversely connected right here, so then you will give a negative voltage here. And whenever you are measuring the output voltage, obviously it is again compared to this common node, whatever voltage you see in the output pin, that's the output voltage. And what are the current directions so far of our assumption? If you see the terminal is non-inverting terminal, the positive terminal we see, we call the current is IP. And for the negative, I mean inverting terminal, the current we call IN. So N for negative, P for positive. And we assume that IP is going inside, IN is also going inside. And here, the output current is basically going inside. But in our assumption, we will find that IP or IN is always zero, basically tends to zero. Now, I have talked about the linear region of the, linear mode operation of the operational amplifier. So you see, this line is basically Vp minus Vn. That means the difference of the two voltages you see here. Like one voltage is applied here, another voltage is applied here. So we call that Vp and Vn. And this axis represents the difference of Vp and Vn. And the vertical axis represents the VCC plus and VCC minus. You see, the operational amplifier operates mainly in this linear region. Then you will see amplified version of the input signal. Now, once it is operating at the saturation region, you cannot go beyond this VCC, right? So even if your formula says that we should get A times this Vp minus Vn at the output terminal, if your VCC is plus 15 volts and your gain times this Vp minus Vn is 20, but your amplified output will not be seen more than 15 because your VCC plus is 15 volts here. That's why we categorize this output in three different regions actually. So minus VCC will be given, you will get the output as minus VCC when the multiplication of the gain times the input voltage difference is less than minus VCC. That means you cannot go beyond this negative VCC. So similar to this positive VCC, you cannot go down to that. Only thing you can vary the gain is in this region, which is basically minus VCC to plus VCC in this range. You see right here. So you can vary the saturation region here, like using some manipulation. You can vary the saturation region if you have, the different VCC. If you have a different VCC, you will, like here, then you will see the saturation region right here. Now, two rules to follow for the basic operation of the operational amplifiers. The rule number one is the Vp and Vn will be equal. So the voltage here at this terminal in the positive and in this terminal at the negative, this point will be equal. And rule number two, as I have already said, that the IP which is going inside this positive terminal and IN which is going inside this negative terminal, inverting and non-inverting terminal, they are equals to zero. So in your circuit analysis, you have to assume this rule number 1 and 2, but there is a different circuit where these two basically sometimes will be zero and sometimes will depend upon the circuit element. So don't mess up with this thing. So always you will see IP and IN is equals to zero, but in some cases Vp and Vn equals to zero, and in some cases it's not zero. So very careful about this one. So what is your assumption about non-inverting amplifier? What do you think it is? Any idea? Okay, So non-inverting amplifier is that amplifier when your the supply voltage, I mean the input voltage is connected to the non-inverting terminal. This is very crucial to understand. Whenever you find an operational amplifier, you see two terminals here, plus and minus, and obviously in most of the cases, you will see at least one input voltage is connected to at least one of these nodes, I mean one of these terminals. So based on the input source connected to non-inverting or inverting terminal, we call that amplifier either non-inverting or inverting amplifier. As I have said in the beginning, so this input voltage Vg is connected to the positive terminal, right? So whenever the input voltage is connected, for example, a sine wave is connected here, and you will see the output voltage that will also be a sine wave with zero phase shift. I mean, input is given in the similar fashion, output you will get in the similar fashion. So if the input is increasing in the positive direction, the output will also be increasing in the positive direction with amplified version. So that is why the output is non-inverted. That means as it is. That's why it is called non-inverting amplifier. But if you connect the Vg instead of this place, if you connect it in the negative terminal, then it is called inverting amplifier. That means if you give an input like input somewhere here, and it is rising in this way, and in the output you'll see it is basically decreasing this way. So now how do you calculate these circuit elements here? So you want to find out the voltage gain or the output voltage of this circuit, right? So you have to remember these two rules already you learned. Vp is equal to Vn and Ip is equals to In equals to 0. And another thing, we already know that the output voltage cannot exceed this VCC, right? We have seen the linear region operation, and we have seen that if the output voltage exceeds VCC in some case, you will not get that reflected in your circuit. Anyway, so for this circuit, you want to find out what is the output voltage. Now think about this node Vn. What is the voltage at Vn? Vn is 0, right? Because it is connected right here immediately at this point, and no current is going inside. Now if we apply a nodal analysis here, we think about every current. This current is going outwards this way, and another current IF is going this way, another current is going IN inside. Now sum of these three currents will be 0. That's why here IS plus IF plus IN is equals to 0. And we already know from rule number 2 that IN equals to 0. That one is equals to 0. That's why we left with IS and IF, right? So to get the IS, how you get the IS? Current is going outside. That means your Vn, you are considering higher. So Vn minus 0. This is connected to ground. So basically this one is Vn minus 0 over Rs, right? Vn minus 0 over Rs for this one. And now for the IF, this is the IF current going from Vn to the output right here. Now as the current we are assuming going outwards, this Vn is higher. So then you are writing Vn minus, the output voltage here is Vo. So Vn minus Vo over this resistance. You know this rule from the nodal analysis, and then this equals to 0. So now we already know that Vn and Vp are equal, right? And here Vn and Vp is equals to Vg. Now if we further simplify that expression and take Vo Rf in the right side, you get right this equation right here. So the Vn and Vp will be equals to Vg. So think about this rule here. Vn and Vp is equals to Vg, because if we think this one is grounded, what is the voltage here is Vz, right? This voltage. And as there is no current flowing through this terminal, so we can think about this Vp is basically the voltage across these two terminals. So this is Vp. So what is the voltage here is Vp. Now Vp is equals to Vn. Even though there is no current flow inside this terminal, but we get how we can find out the Vg. Now from this expression, if we can further simplify this, we will get this final version here, and then again after simplification we get this one. Now if we get this one, we know that V output is equals to 1 plus Rf over Rs. So basically this one is here, not with that. So this one is different. You see. Now your output voltage again is multiplied with Vg. How you can modify the output voltage? You have that parameter Rf, right? And you have the parameter Rs. Now the Vg, for example, this Vg is set to 5 volts. Now if this Vg is equals to 5 volts, that is fixed, your input signal, right? But you want the output voltage a different one. Like you want to manipulate the output voltage. Now how you will design the circuit? So you have Rf and you have Rs here, right? Rf and Rs. Now if Rf become higher, this Rf becomes higher and this Rs becomes lower. Say for example Rf equals to 5 kilo ohm and Rs equal to 1 kilo ohm, then you get 5 over 1, right? So that is 5 plus 1 is equal to 6 times. So if you think this one is 5 and Rs is equal to 1 kilo ohm, then you will get the output voltage for this 5 volts basically 6 times, so 30 volts, right? You are supposed to get 30 volts. But think about it, your VCC, what is the VCC here? If VCC becomes, for example, 15 volts, and your calculation says your output should be 30 volts, but you will not get this 30 volts because it is operating in the saturation region right now. So your output voltage will be 15 volts. So in your circuit analysis, just try to remember this final expression to find out the output voltage, because you'll be needing this to solve any mathematical problem. So how we can make this amplifier as unity amplifier, unity gain amplifier. So you know that from our previous expression, V output is equals to, if we take these two, equals to 1 plus Rf over Rs. Now you want that output to be 1. I'm sorry, I'm using my computer to draw and mouse to draw this thing. That's why it become very messy. Now you have 1 here and you have Rf over Rs. Now if you set whatever value you set here, it does not matter. If this one becomes like this Rs you set it here, but you are setting some value here 0. What is this? Rf. So you are setting this one as 0. Then this term becomes 0. That means your output voltage then will be equals to G. This one is basically Vg, right? So you get that point. whenever you are setting that, I mean, you are shorting these two terminals, right? The input terminal is shorted with the output terminals. That means there is no feedback resistance here. So in that case, RF becomes zero, and whatever is value you set RS, it does not matter. The output voltage will be equals to input voltage. That means what is your gain here? Your gain is here 1. And that is why this one is called unity amplifier. And that is also called voltage follower. Why it is called voltage follower? As it is the unity amplifier, so whatever is the change in input voltage, it will appear in the output voltage just directly. If you change it 1 milliamps, 1 millivolt increase of the input voltage, VG here, the 1 millivolt increase you will see directly here. That means your VG, for example, 5 volts here. For this circuit, unity gain, always it will be 5 volt, right? So that's the key takeaway of this unity amplifier. And that is used in case of buffer, like buffer circuit. Okay, so the voltage for isolate one circuit from the another. It's really difficult to see here. Okay, so this circuit, voltage follower circuit, is used in cases whenever you need to isolate one circuit from the another. Okay, you are using this unity amplifier, you are giving some 5 volts input here, and you know that no current is flowing inside this, right? That means IP and IN equals to 0. So whatever else value you set here, whatever voltage source you set here, there is no current going inside. That means no impact of this in the output circuit. That's why your output circuit is kind of isolated from the input circuit. And this is called also like a buffer circuit and used in different circuit elements, especially in control circuits. Now, this is an example where it is used as a buffer circuit. So if you close this circuit here, switch here, so the voltage will be changed across this, maybe across this load, this I mean 1 ohm. Because whenever you're turning this switch, you are like just closing that circuit, you have a change in current, and that change in current is causing a change in voltage in this element. Now, instead of using this this kind of circuitry, if we use a unity, I mean voltage follower circuit right here, so it is always connected, then you will not face any voltage change right here. But you can control the, I mean, you know that, right? There is no current flowing from this terminal to the output, basically. Now the inverting amplifier. So we have already known about the non-inverting amplifier, where the input voltage is connected to the non-inverting terminal. Now you have VS, which is directly connected here with, of course, with a series resistor here, is connected to the inverting terminal of the amplifier. Whenever you see this kind of circuit, like only one voltage source there, and there is no voltage source with the other, that is grounded, obviously you will identify this one as an inverting amplifier. Now, how do you determine the output voltage for this kind of circuit? Now, at this terminal, like at this node Vn, if we apply the nodal analysis, at first use the KCL, right? So all the currents are going outwards, or maybe all the currents are going inwards, it doesn't matter. So now IS plus IF plus IN is equals to 0, for example. So if you think the current is going inside, this current is going inside, this current is going outside, basically what is happening? This is kind of a similar analysis of the previous circuit we have seen so far. Now, IS plus IF, we are thinking direction is inward now. So think about it is inward, right? Now, if this current is going inside, what is the current? How you determine the current? So that is, okay. So this voltage Vs minus Vn, okay, the notation is basically a little bit bad here. I have to correct it. So keep it as it is. It will be better to understand. Because we are saying Vn minus Vs over Rs. So Vn is higher, and then Vn minus Vs, then current is obviously going outwards. So this one becomes this one, right? And If, this If becomes this one. So If is basically Vn minus Vo over Rf. So the difference in these two voltages, and then divide with that resistance Rf. Now, this Vn and Vp, what is the value of Vn and Vp? Now, you see this terminal is directly connected to the ground, right? So that means this is 0 voltage. So if this voltage is 0, your Vp is equals to 0, right? If your Vp equals to 0, then obviously your Vn is also 0, because we already know Vp is equals to Vn. So we got that this one is becoming 0. Now, obviously, following rule number 1, your Vn will also be equals to 0. Now put the Vn 0 right here, and you will get this expression. Just put 0 here. And finally, you get minus Vs over Rs is equals to Vo over Rf. So this is your final expression here. Now, if we further simplify it, so output voltage is equals to minus of Rf over Rs times Vs. So what's important thing to take away here? The output voltage of inverting amplifier is inverted. That's why you see this negative sign here. You see, because of this inverting. Another thing, the output voltage you can also change, and how much output voltage you want, it can be varied or it can be modified according to your design. This RF and RS. Now, if you increase this RS and RF and decrease this value, then you will get higher gain, right? And vice versa. And again, if you put these two equals to like 1, that means you are making these two 1 kilo ohm and 1 kilo ohm. If you put this RF and RS equal to 1 kilo ohm, then again it is a kind of voltage, kind of similar to the voltage follower, right? So minus Vs, but it is in inverting voltage follower kind of. You see the previous one? So this one is a voltage follower, but output voltage is non-inverting, right? Input is equals to Vg directly. Now, for the case of this one, if you have 1 here, 1 kilo ohm here, 1 kilo ohm here, that means similar voltage in these two places, you will see output voltage is equals to input voltage, but inverting. So, this is another kind of amplifier. Any questions so far you don't understand, please let me know. You can see my screen, right?
Yes, we can
Yes,
see
sir.
it.
Okay, so no questions so far, right? Okay, that's good. Now, the thing here, if we find this circuitry like this inverting amplifier, and instead of connecting one resistor here, if we can connect another resistor here with another source, then another resistor here and with another source here, how you will get the output voltage? That's what right here. The same circuit, only difference is that you have multiple inputs here. You see this one, VA, VB, and VC. Now, all of them are connected right this point, right, this node. So how you determine the VN now? Apply the similar kind of rule, like VN minus VS. So think about every current is going outside. This current, and obviously this current. So three currents going outside, and also think about this current is going this way, and another current is going this way. So apply, and this is the same node, right? In this same node, if you apply KCL and all the currents are going outside, so sum of all the currents is equals to 0. Now, how you find out the current in this through this resistor, right? So VN minus VA over RA, that is this one, the first one for this current right here. And similarly, Vn minus Vb is your another branch current here, like current through this way. So this one is here, and you get one here, and you get the last one. Last one is this one. You see for this one. So Vn minus Vo over Rf, and this In already we know from the rule is equals to 0. Right? There is no current flowing inside. Now, if we further simplify this one, and this Vp, what is the value of Vp? Anybody else can give me the answer? So 0, yes. So as Vp is equals to 0, what is the voltage of Vn? That's also 0, right? Because you know the rule number 1, Vp is equals to Vn equals to 0. Now put all these Vn equals to 0. Then you finally come up with this circuit expression. And what is the difference between this one and the previous one we learned here? It's all the same, except you are kind of adding all the voltages, right? So if you think about, there is no all these two elements, only first one is there, then it is similar to this, this inverting amplifier. That means RF over RS times VA. Now what are we doing here? As we have more than one voltage source and resistors here connected in parallel at the same node, we're adding more elements right here. We are summing them up. That's why this is called a summing amplifier. You understand that point, right? Why is this called summing amplifier? We can further simplify this one in a way. For example, RA, RB, and RC is equals to RS. Think about RA, RB, and RC, all three are equals to RS. Then how you get that output voltage? So you will get the output voltage is equals to minus, and also think about this VA, VB, and VC is equals to, all of them are equal. Think about all of them are equals to, say VS. You got that point, right? What I'm assuming, this RA, RB, and RC all are equal, and VA, VB, and VC all are equal. Now, you come up with this RF over RS, RF over RS times VC, RF over. So basically, you are finding 3 times RF over RS times VS. So you are giving input here like VC, VS, VS, VS. And you are giving input in 3 different combinations, like I mean one combination, but in 3 different brands here, RB, RA, and RC. That's why your output voltage is now 3 times. So that's the visualization, how you get the summing amplifier. You are summing them up. So based on the different voltages and different resistors you are putting here, the signals, input signals becoming different, but still they are adding them up at the output in an inverse manner. Actually, there is still the negative sign here. Any questions to understand? Okay. So this one already simplified that circuit that I already just told to you. Instead, what are they trying to do? This RF and RS making equal. Now further, this RF and RS, if we make equal, then it is basically 3 times of the input voltage. Now, from the circuit point of view, if we think these 3 voltages are different, but these resistances are equal. So these are different, like VA, VB, VC, but these resistances RB, RA, and RC are equal to RS. Then you come up with this expression. Now, if you put any of these resistance is equals to like RF, where RF is equals to RS, then you come up with this, right? So that is also another point of understanding, like this is a summing amplifier, which is basically summing up all the input voltages. Now, if all the input voltages are equals to Vs, then you come up with 3 times of Vs, right? And that's what I have told you here. If RF and RS becomes to, these two becomes to 1 kilo ohm or something, then output voltage will be minus 3 of Vs. However, you only need to remember this expression, that's final expression, and how you get that, and also how you get this expression. I'm not sure whether this will be tested in your exam. Just try to remember these things. And anyway, can you please tell me what kind of amplifier is this one? So far you have studied this right side. Inverting, non-inverting, summing or something.
I believe that would be a non-inverting.
That's correct. This is non-inverting because it is connected to the non-inverting terminal here, like the input voltage here. Okay, now you already know the expression for the non-inverting amplifier. Now, from these circuit elements, if we give you this Vs is equals to something, say 5 volts, then you can find out the V output, right? Because you already know this Rs is equals to 3. You already know Rf equals to 2. So, and you have the input voltage 5 volts. Then from this expression, you can find out the output voltage, right? So it's up to you. You calculate that and you let me know what is the output voltage here. That's very simple. What about this one? Inverting, non-inverting, or summing, or difference? Inverting. That's right. I got the chat messages. Inverting because it is connected to the inverting. Now, apart from this inverting and non-inverting and summing amplifier, you have another amplifier that is called a difference amplifier, where you will see both of the input terminals are connected to a voltage source. Anyway, so this is actually inverting amplifier, and you already know the expression here. Now, if all the parameters are given here, you can easily find out like RF from this side, because you are given with output voltage, you are given with input voltage, and this resistance is also given. So just put all of them here in this expression and you will find out the RF. Okay, so I have this circuit. So what will be the output here? Number 1, 2, 3, or 4, or 5. What will be the output here? At first, tell me what kind of circuit is this? What kind of amplifier circuit is this? You can unmute yourself and talk to me, or you can write out in the chat box. I know the time is already up, So if you have any other task to do, any class to attend, please, you can leave. I'll just take a couple of more minutes, like 5 minutes maybe.
It's an inverting amplifier.
That's inverting amplifier, but apart from inverting, it is summing amplifier because you have two different voltage source, right? So now which one will be the output here? It is summing up these two voltages.
There'll be option 1.
Why? You are saying this is inverting. Obviously, it is associated with, so V output will be equals to something negative, right? Because it is inverting. Now, what will be inside here? V1 plus
V1
V2.
plus V2.
So basically, this is coming up with this one, right? So is it clear? This
That
is a
makes sense.
summing. Okay.
I have a question on the homework if you have a minute.
Sure. Which homework?
The newest one. It's just about how a problem's written, not really how to do it.
Okay, I have not looked at it. Okay, go ahead. Okay, let me finish
So,
this one just real quick.
sure.
So there is nothing here. Only one thing is difference amplifier is given here, and the expressions are given here how you can determine the output voltage. So what is the difference amplifier? If you see two inputs have the like here connected to the input inverting and non-inverting, then it is a difference amplifier. However, these are the materials you can go through YouTube video tutorials. Basically, you want to know the inverting, non-inverting, and summing or voltage follower amplifier. You want to know more? Please go through this one. Okay. Thank you very much from the lecture side, and I'll see if you have any question. Like, what question do you have?
So on problem 3 in the homework, it says for a difference amplifier, and it gives some values for R1 or for R2, 3, and 4. And my question is, there's no schematic showing it. So how do we know which resistor R2 is and which resistor R3 is?
Okay, let me find out the homework 3. Homework 3 problem. So, which problem you said? Number 3?
3, that's correct.
Okay, so for a difference amplifier circuit that can perform the following operation, VO is equals to VS2 minus V. Given that R2 is this, R3 is this, and R4 is this. Find VS1 and R1. Okay.
My question would just be is how do I know which resistor R2 is and which resistor R3 is?
Okay, I understand there is no clarification here, right? No more circuit, only one, this one. So problem 1, find VO. This. There is no other circuit? No. Okay, so I'll look into it and I'll try to see if any circuit I can give to you, okay?
All right, perfect. Thank you.
I'll talk to the professor if he already has any particular problem he is referring to.
Okay.
Other than that, I'll make up something to you. Yeah.
Thank you.
Okay. No problem. Any more questions? Okay. Then thank you so much. I'll see you in next week. Bye.